Blueprint for Mars Colonization, breakdown of NASA's $30 billion budget allocation and 5-phase implementation strategy by 2032. Introduction. NASA has embarked on an ambitious plan to establish a human presence on Mars by 2032 with a strategic budget allocation of $30 billion. This plan is structured around a 5-phase implementation strategy designed to address the numerous challenges associated with interplanetary colonization. The following report outlines the phases involved, the budget allocation, and the key technologies and missions that will enable this monumental goal. Overview of the 5-phase implementation strategy. Phase 1, Research and Development 2024 to 2026. The first phase focuses on critical research and development efforts with an allocation of approximately $5 billion. This phase aims to advance technology necessary for human survival on Mars, including life support systems, development of systems that can provide air, water, and food for astronauts, radiation shielding, innovations to protect against cosmic and solar radiation, which poses significant risks to human health. Sustainable habitats, creation of structures that can withstand the Martian environment and provide a livable space for astronauts. Additionally, this phase emphasizes in situ resource utilization (ISRU) technologies which will allow astronauts to use Martian resources for fuel and water, reducing the need for supplies from Earth. Phase 2, Robotic Missions 2027 to 2028. Following the R&D phase, NASA plans to conduct a series of robotic missions to Mars costing about $7 billion. These missions will involve scouting locations. Robotic drones and rovers will explore potential landing sites for human missions, assessing the environment for safety and resource availability. Technology testing. These missions will serve as a platform to test the technologies developed in Phase 1, ensuring they are operational under Martian conditions. The data collected during this phase will be crucial for planning subsequent human missions. Phase 3, Human Precursor Missions 2029. In 2029, NASA will conduct crewed missions to the Moon with an estimated budget of $6 billion. The objectives include simulating Mars conditions. By operating on the Moon, astronauts can test life support systems, habitats, and other technologies in a closer and more accessible environment. Training astronauts. These missions will also serve to train astronauts for the unique challenges they will face on Mars, including extended stays and operational management of life support systems. This preparatory phase is essential for minimizing risks before the first human landing on Mars. Phase 4, Human Landing on Mars 2030. The fourth phase is the most critical as it involves the first human landing on Mars planned for 2030. With an investment of approximately $8 billion. Key components include transportation, utilizing the Space Launch System (SLS) and Orion spacecraft for astronaut transport to Mars. Landing operations, development of landing systems to ensure a safe arrival on the Martian surface. This phase marks a significant milestone in human space exploration. Phase 5, Establishing a Sustainable Presence 2031 to 2032. The final phase, extending from 2031 to 2032, focuses on establishing a permanent and sustainable human presence on Mars with a budget of $4 billion. Goals include permanent habitats, construction of long-term living quarters for astronauts ensuring comfort and safety. Agricultural systems, development of systems to grow food on Mars, which is critical for long-term missions and reducing reliance on Earth supplies. This phase aims to create a self-sustaining colony capable of supporting human life indefinitely. Common key points across sources. Budget allocation, consistently reported at $30 billion. With detailed breakdowns for each phase. Focus on technology development, emphasis on life support and resource utilization technologies as pivotal for Mars survival. Robotic precursor missions, recognition of the necessity of robotic missions to gather data and validate technologies before human exploration. Differences between sources. While the overall strategy and budget remain consistent across various sources, some differences emerge in specific details. For example, certain sources highlight international collaboration, the potential for partnerships with other space agencies such as the European Space Agency (ESA) and private companies in space exploration. Specific technologies, variations in the emphasis placed on different technological innovations such as advanced propulsion systems or habitat designs. Timeline of events. 1. 2024 to 2026, Research and Development Phase focusing on technology advancement. 2. 2027 to 2028, Robotic missions to Mars for environmental assessment and technology testing. 3. 2029, crewed lunar missions to trial technologies and train astronauts. 4. 2030, first human landing on Mars. A landmark achievement in space exploration. 5. 2031 to 2032, establishment of a sustainable human presence through habitat and agricultural development. Conclusion. NASA's blueprint for Mars colonization represents a meticulously planned approach to one of humanity's most significant challenges. By allocating a substantial budget and implementing a phased strategy, NASA aims not only to land humans on Mars but also to ensure their long-term survival through advanced technology and thorough preparation. The iterative nature of this plan allows for learning and adaptation, essential elements in tackling the complexities of interplanetary colonization. As we move closer to the proposed timelines, the world watches with anticipation for the dawn of a new era in space exploration. The content presents a detailed outline of NASA's strategy for Mars colonization, emphasizing a $30 billion budget and a structured 5-phase plan leading up to 2032. Here are some counterintuitive insights derived from the information provided. 1. Heavy emphasis on R&D despite historical context. While NASA has a rich history of space exploration, the significant allocation of $5 billion towards research and development R&D in Phase 1 might seem counterintuitive given past achievements. It suggests that the technological challenges of colonizing Mars are far more complex and varied than those faced during previous missions such as the Apollo program. This indicates a shift from merely landing on celestial bodies to creating sustainable life-supporting systems in hostile environments. 2. Prioritization of lunar missions over immediate Mars exploration. The decision to conduct crewed lunar missions in Phase 3 as a precursor to Mars exploration could appear counterintuitive. Many might expect direct missions to Mars to be prioritized given the ultimate goal. However, this strategy highlights the understanding that the Moon presents a more manageable environment for testing technologies critical for Mars, thereby reducing the risk of failure during the more ambitious endeavor of a Mars landing. 3. Robotic missions as pioneers for human presence. The allocation of approximately $7 billion for robotic missions in Phase 2 intended to scout and assess Martian locations for human landings contradicts the common expectation that human exploration would take precedence. Instead, it underscores a careful and methodical approach to ensure that when humans do arrive, they will have a well-informed understanding of their surroundings and the necessary resources available. For sustainability focus despite initial costs, the final phase's budget of $4 billion for establishing a sustainable human presence might seem low compared to the previous phases, particularly the $8 billion allocation for the human landing. This could suggest that initial costs for establishing a human presence might be less than anticipated, or it may reflect an assumption that ongoing operations can be funded through other means such as partnerships or commercial ventures. This approach challenges traditional views on the high costs associated with long-term space habitation. 5. International collaboration not explicitly highlighted. The summary notes a difference in emphasis on international collaboration among various sources, with some stressing its importance more than others. This could be counterintuitive, as many would expect a mission of this magnitude to inherently involve global partnerships given the shared human interest in space exploration. The lack of a strong emphasis on collaboration in this specific plan may indicate a potential oversight or a strategic decision by NASA to retain control over the mission's direction and funding. 6. Iterative learning approach. The phased implementation strategy, which allows for iterative learning and adaptation, contrasts with the traditional linear planning approaches often associated with large-scale projects. This suggests a recognition of the unpredictable nature of space exploration and an acknowledgement that flexibility may be crucial for success, which might seem at odds with the structured nature of government-funded projects. In summary, the blueprint for Mars colonization reveals several counterintuitive aspects that challenge conventional expectations about space exploration technology development and mission planning. The strategy reflects a nuanced understanding of the complexities involved in establishing a sustainable human presence on Mars. In the analysis of NASA's blueprint for Mars colonization, several significant elements may be overlooked by the general public, yet they hold critical importance for the success of the entire mission. Here are the key overlooked aspects and their significance. 1. In situ resource utilization (ISRU). While the concept of ISRU is often mentioned, the depth and implications of its implementation can be easily underestimated. ISRU involves extracting and utilizing local resources on Mars such as water, ice, and carbon dioxide to produce fuel and oxygen. This technology is crucial because it minimizes the amount of supplies that must be transported from Earth, reducing costs and increasing mission feasibility. Significance: the success of human life on Mars hinges on effective ISRU systems. If these systems fail or prove less efficient than expected, it could jeopardize the sustainability of human presence on Mars. Developing robust ISRU technologies in the early phases ensures that astronauts can create life-sustaining resources locally, which is vital for long-term colonization. 2. Psychological and physiological preparedness. NASA's plan includes technological advancements, but the psychological and physiological aspects of long-term space missions are often underemphasized. The isolation, confinement, and microgravity could adversely affect the mental health and physical well-being of astronauts. Significance: understanding the impacts of long-duration spaceflight on human psychology and physiology is essential for mission success. If NASA does not adequately prepare for these issues, it risks having a crew that is unfit for the challenges of Mars colonization, potentially leading to mission failure. This aspect requires ongoing research and integrated solutions such as habitat designs that incorporate social and recreational needs. 3. International collaboration. While some sources briefly mention the importance of partnerships with international space agencies and private companies, the depth of these collaborations is often skimmed over. Collaborative efforts could enhance technological development and share the financial burden. Significance: international collaboration can leverage expertise and resources, accelerating progress and reducing risks. The complexity of Mars colonization demands a diverse set of skills, technologies, and funding sources, making alliances critical for achieving shared goals. Overlooking this could lead to missed opportunities for innovation and resource optimization. 4. Technology testing on the Moon. The decision to conduct human precursor missions to the Moon is significant but often overshadowed by the focus on Mars. This phase serves as a crucial testing ground for Mars-related technologies. Significance: the Moon provides a more accessible environment to test life support systems, habitat designs, and operational protocols before committing to the more complex Martian environment. This preparatory step is vital for risk mitigation and learning, ensuring that NASA can address challenges in a controlled setting before embarking on the more challenging Mars missions. 5. Sustainability beyond initial colonization. While the final phase focuses on establishing a sustainable presence, the long-term sustainability strategies, including agricultural systems and resource recycling, may not receive the attention they deserve. Significance: sustainability is not just about establishing a presence, it is about ensuring that presence can thrive over decades or centuries. Innovations in closed-loop life support systems, food production on Mars, and waste recycling will determine the viability of a human colony. Failing to prioritize these elements could lead to dependency on Earth, undermining the goal of self-sufficiency. 6. Environmental considerations and planetary protection. NASA's plan does not sufficiently emphasize the environmental impact of colonization, including planetary protection protocols. The ethical implications of terraforming or altering Mars could have long-term consequences for scientific research and the integrity of Martian ecosystems. Significance: as humanity ventures into space, it must consider the ethical implications of its actions. Responsible exploration that prioritizes planetary protection is essential to maintaining the scientific value of Mars. Overlooking these considerations could lead to irreversible changes to the Martian environment and a loss of potential scientific discoveries. 7. Backup plans and contingency strategies. The detailed phases outline a clear path forward, but the absence of comprehensive contingency plans for potential failures in technology, mission timelines, or financial shortfalls is a critical oversight. Significance: space missions are inherently risky with many variables beyond human control. Establishing robust backup plans and contingency strategies is essential for mitigating risks. This could involve alternative technologies, mission redesigns, or additional funding sources. Ignoring this aspect could result in mission delays or failures if unexpected challenges arise. 8. Public engagement and support. The plan does not extensively address how NASA intends to engage the public and maintain interest in the Mars Colonization initiative. Public support can be vital for securing funding and political backing. Significance: engaging the public and fostering a sense of shared mission can drive enthusiasm and support for Mars colonization. It can also inspire the next generation of scientists and engineers, ensuring a continuous flow of talent into the space sector. Failing to prioritize public engagement could lead to a lack of support, which is critical for the long-term viability of such ambitious projects. Conclusion: the pathway to Mars colonization involves complex technical, social, and ethical considerations that extend beyond the immediate technological and budgetary aspects outlined in NASA's plan. By focusing on these often overlooked factors, such as ISRU, psychological preparedness, international collaboration, sustainability, planetary protection, contingency planning, and public engagement, NASA can enhance its chances of successfully establishing a human presence on Mars. Addressing these elements holistically will be crucial for not only achieving the initial landing but ensuring a thriving long-term colony that can operate independently and responsibly on another planet. 1. Budget allocation and financial strategy. The $30 billion budget allocation is a cornerstone of NASA's Mars colonization plan. This financial strategy is not only crucial for the execution of the various phases but also reflects the prioritization of technological development, robotic missions, and human exploration. The breakdown of the budget across 5 phases: research and development, robotic missions, human precursor missions, human landing on Mars, and establishing a sustainable presence, illustrates a methodical approach to resource allocation. Each phase has specific financial commitments that correspond to its goals, ensuring that funds are directed toward the most critical needs at each stage of the mission. The budget's emphasis on technology development and sustainability is particularly noteworthy, as these factors are essential for long-term human survival on Mars. 2. Phased implementation strategy. NASA's 5-phase implementation strategy is a well-defined roadmap that outlines the steps required to achieve successful Mars colonization by 2032. Each phase builds on the previous one, allowing for iterative learning and adaptation, a key factor in the success of complex space missions. The progression from R&D to robotic missions and finally to human exploration ensures that each phase informs the next. This phased approach not only minimizes risks associated with human spaceflight but also enhances the likelihood of mission success by addressing technological and environmental challenges incrementally. The inclusion of human precursor missions on the Moon as a preparatory step for Mars is particularly significant as it allows for the testing of life support systems and habitat technologies in a more accessible environment. 3. Technological development focus. The emphasis on technological development, particularly in areas like life support systems, radiation shielding, and in situ resource utilization (ISRU), is a critical component of the Mars colonization strategy. These technologies are essential for ensuring the safety and sustainability of human life on Mars. For instance, ISRU will enable astronauts to use local resources for fuel and water, significantly reducing the amount of supplies that need to be transported from Earth. The allocation of approximately $5 billion in the R&D phase specifically for advancements in these technologies underscores their importance in the overall mission framework. This focus on innovation not only addresses immediate survival needs but also lays the groundwork for the long-term goal of establishing a self-sustaining human presence on the planet. 4. Robotic missions as precursor to human exploration. The planned robotic missions Phase 2 serve as a critical precursor to human exploration. By sending drones and rovers to assess the Martian environment and test technologies developed in Phase 1, NASA can gather essential data that will inform human landing strategies. The allocation of $7 billion for this phase highlights the importance of data collection and environmental assessment in reducing risks associated with human missions. These robotic missions will provide insights into the planet's surface conditions, resources, and potential hazards, enabling astronauts to make informed decisions once they arrive on Mars. The reliance on robotic technology before committing to human exploration reflects a prudent approach to interplanetary colonization, emphasizing safety and preparedness. These 4 points: budget allocation and financial strategy, the phased implementation strategy, technological development focus, and the role of robotic missions, are integral to understanding NASA's comprehensive plan for Mars colonization. Each component plays a vital role in ensuring the mission's success and the establishment of a sustainable human presence on the Red Planet. Famous historical cases similar to NASA's Mars colonization blueprint. 1. The Apollo program, 1960s to 1970s. The Apollo program was NASA's pioneering effort to land humans on the Moon and return them safely to Earth. Initiated in response to the space race, Apollo's budget exceeded $25 billion, equivalent to over $150 billion today. And it involved a multi-phase approach that included extensive research and development, uncrewed test missions, and eventually crewed lunar landings. The program's iconic achievements, particularly Apollo 11 in 1969, demonstrated the feasibility of human space exploration and laid the groundwork for future missions beyond Earth. Like the Mars colonization plan, Apollo involved significant international collaboration, technological innovation, and a focus on sustainable human presence in space. 2. The International Space Station ISS program, 1998-present. The ISS represents a collaborative effort among multiple nations, including NASA, Roscosmos, ESA, JAXA, and CSA, to maintain a permanent human presence in low Earth orbit. The program has involved a substantial budget and an incremental implementation strategy that included the design, construction, and ongoing maintenance of the space station. The ISS serves as a platform for scientific research and technology development, which parallels NASA's focus on using robotic precursor missions and R&D for Mars colonization. The lessons learned regarding life support systems, international cooperation, and long-duration human missions in space are directly applicable to the challenges posed by Mars colonization. 3. The European Space Agency's Mars Express mission, 2003-present. Launched in 2003, the Mars Express mission marked ESA's first mission to Mars and has provided critical data about the Martian environment. The mission's phased approach included a series of scientific objectives, including mapping Mars' surface, studying its atmosphere, and identifying water resources. The successful deployment of the Mars Express orbiter and its subsequent findings have informed future missions and explorations of Mars. Similar to NASA's strategy of using robotic missions to gather data before human landings, The emphasis on in situ resource utilization and environmental assessment in both the Mars Express and NASA's plans highlight the importance of thorough preparation for human colonization efforts. Future outlook: predictions for Mars colonization by 2032. As NASA embarks on its ambitious plan for Mars colonization with a structured $30 billion budget and a 5-phase implementation strategy, the future holds immense possibilities and challenges. By 2032, we can anticipate several key developments in space exploration technology, human adaptation, and international collaboration, all of which will shape the landscape of Martian colonization. 1. Technological advancements. By 2032, we can expect significant advancements in technology driven by the initial phases of NASA's plan. Innovations in propulsion systems, life support, and habitat construction will emerge from the R&D phase 2024 to 2026. This technological evolution will not only facilitate human travel and survival on Mars but will also have applications on Earth, enhancing our capabilities in sustainability, energy efficiency, and resource management. 2. Successful robotic missions. The robotic missions planned for 2027 to 2028 will likely yield critical data about Mars' environment, revealing vital information about potential landing sites and resources. These missions are expected to demonstrate the effectiveness of in situ resource utilization (ISRU), allowing future missions to use Martian materials for fuel and water. The success of these early missions will build public and governmental support for manned missions. 3. Human precursor missions to the Moon. The planned human precursor missions to the Moon in 2029 will serve as a testing ground for technologies intended for Mars. These missions will not only simulate Martian conditions but also refine operational protocols for human spaceflight. The lessons learned here will be crucial in minimizing risks for the first crewed mission to Mars. 4. The first human landing on Mars. The anticipated human landing on Mars in 2030 will be a monumental achievement for humanity. It will mark the first time humans set foot on another planet, fostering a sense of unity and purpose. This event is likely to spark increased interest in STEM fields and inspire a new generation of scientists, engineers, and explorers. 5. Establishing a sustainable presence. By the end of 2032, NASA aims to establish a sustainable human presence on Mars. This will involve creating habitats capable of supporting life, developing agricultural systems for food production, and building the necessary infrastructure for energy and water. The success of this phase will depend on the effective implementation of technologies developed in earlier phases, as well as ongoing research into Martian ecology and geology. 6. International collaboration. The colonization of Mars will likely be a collaborative effort involving multiple space agencies and private companies. Countries such as China, India, and those within the European Space Agency (ESA) are expected to play significant roles in supporting Mars missions. This international collaboration could lead to shared resources, knowledge exchange, and a united front in addressing challenges associated with space exploration. 7. Societal impacts and ethical considerations. The endeavor to colonize Mars will raise important ethical questions and societal implications. As humanity extends its reach into space, discussions about planetary protection, the rights of potential Martian life forms, and the long-term sustainability of colonization efforts will be paramount. By 2032, these discussions may lead to the establishment of international agreements governing the exploration and utilization of Martian resources. 8. Economic opportunities. The development of a human presence on Mars will also open up new economic opportunities. The space industry is expected to grow with investments in technology infrastructure and research. This growth could spur innovation on Earth and create jobs, particularly in sectors related to aerospace, robotics, and sustainable technologies. 9. Psychological and health research. Understanding the psychological and physical impacts of long-duration space missions will be critical. By 2032, NASA and other institutions will likely have conducted extensive research on the effects of microgravity radiation exposure and isolation on human health. This knowledge will be essential for ensuring the well-being of astronauts and colonists on Mars. 10. Public engagement and inspiration. The journey to Mars will capture the public's imagination, fostering a renewed interest in exploration and discovery. By 2032, we can expect enhanced public engagement through media educational programs and outreach initiatives. The narrative of human exploration will inspire global audiences, encouraging a sense of shared destiny as we venture into the cosmos. Conclusion. In summary, the future of Mars colonization presents a tapestry of technological innovation, international cooperation, ethical considerations, and societal impact. NASA's structured approach, including a $30 billion budget and a 5-phase implementation strategy, sets the stage for significant milestones by 2032. The successful execution of this plan could redefine humanity's relationship with space and lay the groundwork for a new era of exploration and discovery.